Okay, good afternoon. We will continue our discussion on measurement of void fraction. After that, we will shift towards the interface reconstruction techniques. So, in terms of void fraction, we have mathematically seen that void fraction we can classify either as one-dimensional, two-dimensional, or three-dimensional. And in terms of the measurement techniques, we have to know the phase density function. If we know the phase density function, then we can easily estimate the value of the void fraction. And in terms of different measurement techniques, we have already talked about the radiation attenuation based techniques, and then we have talked about optical techniques for measurement of phase distribution function. After that, we discussed the resistance impedance based methods as well as only impedance based methods. Okay, and in case of impedance based methods, we were able to directly get the value of void fraction as output depending upon the measured resistance. Okay, now we will talk about one more method which is based on the electrical capacitance measurement. So typically, whenever we are having multiple fluids available, then all the fluids are having their different dielectric constants. So depending upon the different dielectric constants, if you have fully one fluid within the capacitance plates, then we will be having some different value of capacitance, and if we have other fluid, then the obtained value will be different, and ultimately this value is actually related in terms of the void fraction. For example, capacitance between any two electrodes is a function of K, where K is some coefficient, and zeta G, this is nothing but dielectric constant of the gaseous phase, into epsilon. Epsilon is actually value of void fraction. Okay, void fraction or fraction of the gas present in the mixture. And zeta L is dielectric constant of the liquid phase, and 1 minus epsilon is fraction of liquid phase. Is this point clear? So this is the governing equation. Now in this equation you can see when the value of epsilon will be changing, when the value of void fraction will be changing, then corresponding to that we will be having changes in the overall capacitance of the system. And this K, which is coefficient of void fraction, it is typically the function of the geometry, what kind of geometry for different electrodes we are using, and it is also the function of flow regime in which we are actually operating. Okay, so you can see now, based on this formula and the value of this coefficient, we can have different arrangement. One of the arrangement is flat plate electrode. So I have one flat plate electrode at the top, one flat plate electrode at the bottom, and then these two electrodes are actually connected to measure the capacitance, and in between this, depending upon the void fraction, say these are my gaseous voids present in liquid, depending upon the magnitude of the void fraction, we will be having different value of the capacitance. However, one important point is this value of capacitance for corresponding value of epsilon can be in different phase distribution. For example, these four bubbles are present in this liquid phase are creating epsilon as the value of void fraction. Same value of void fraction can also be created by presence of a larger slug near the top of the bubble. Okay, so in these two scenarios, though value of void fraction is same, so corresponding to this, we will be expecting that our value of capacitance should be same. However, there will not be exactly the same value of capacitance, but value of capacitance may change. So the factor K over here actually defines the coefficient which changes for different flow regimes. So because of this purpose, because not only the distribution of the phases, like not only the void fraction, but their individual locations within the pipe also slightly modifies the value of the capacitance. That's why whenever we are using this capacitance based probe, we have to always calibrate this probe for a particular flow regime in order to find the value of this. Is this one clear? So this coefficient needs to be calibrated for each and every flow regime. So it will be having specific value corresponding to a particular flow. Okay.
These methods like these give the only bubbles present in the, like, find the bubbles present or not in the liquid, or
Yes.
can differentiate between two liquid like kerosene and water.
It can differentiate if their dielectric constant is significantly different. Because in this particular method, we are talking about now the capacitance based approach. And capacitance value is a function of dielectric constant and phase fraction. So if dielectric constant of that particular liquid combination is significantly different, it can be used.
So for some like optical probe method,
Yes.
in that it will only detect the bubbles forming or voice.
Optical probe method will be working fine if you have the operating range of N1 and N2 significantly large. Okay, so for example, N1 was the refractive index in the medium 1, N2 was the refractive index in the medium 2. And if you recall, for large range of medium 1 to 2, what we have done? We have determined the critical value of angle of incidence. If critical value of angle of incidence, if angle of incidence is greater than the critical value for a given design, then it can be used for different, even for liquid cases, for different refractive cases.
So bubble have the refractive mix of both because
Yes. Okay, so this first type of device is actually flat plate electrode. In second type of device, in order to improve the sensitivity of the system, multiple electrodes are taken. So you can see now electrodes are in curved orientation over the pipe geometry, and these set of electrodes are connected together, and in the bottom side also we have other set of electrodes. Okay. So this first and second, which is flat plate electrode and multi-electrode probe, these typically are used for measurement of two-dimensional void fraction. Why these are giving two-dimensional void fraction? Can you tell me? Typically at the moment we are assuming that the width of the plate normal to the plane is small, and second important point is it is not giving me the phase density function at any individual specific location. It is giving the change in value of capacitance depending upon the amount of phases present within the pipe cross section. So as it is talking about the complete pipe cross section, and for the entire pipe cross section, depending upon the amount of gas present, it is changing its capacitance value. That's why it is giving us what type of void fraction? Two-dimensional void fraction. It cannot give us the value of local in situ void fraction, because we are not measuring anything as a function of position. Whatever capacitance we are measuring, that is the global value for the complete cross section. Is this one clear? Then, so it means that this can only give you the idea about the void fraction. It will not give you any idea about distribution of the phases. It cannot tell that where bubble is present, because we are explicitly not measuring the phase distribution function. Is this one clear? Now, the third arrangement could be helical wound probe. So in case of helical wound probe, this light gray color is representing one type of electrode, and the dark gray color is representing other type of electrode. And these are wounded on the pipe along a certain length portion of the pipe. That's why corresponding to these, whatever the value I will be getting, that may give me the idea of volumetric void fraction or three-dimensional void fraction. Is this one clear? Similarly, there can be another arrangement like concave plates arrangement. So for example, these curved plates are used, alternate curved plates are used instead of using the flat plate arrangement. Okay. Now, whatever the discussion we have done till this stage, our major idea or major interest was to estimate the value of void fraction. Okay. Once we know the value of void fraction, as just now I gave you one example, the same value of void fraction can also be achieved either by using this type of distribution of bubbles or by using a single slug bubble present, and then below I am having the other gas present. Okay, so in both the situations I can have same value of the void fraction. But one important parameter will be different. If you see in this type of situation, the interfacial area between the gas and liquid phase flow will be different for the two combinations. And in case of multi-phase flow, interfacial area between the gas and liquid is one of the important consideration in determining various mass, heat and momentum exchanges. Okay, because if interfacial area is large, then we will be having fast reaction, fast exchange of mass, momentum and energy, and in case interfacial area is less, then exchange of these quantities will be slow. Okay, and in certain heat transfer applications, knowing the flow pattern is also very important, because you can take one example. Say you have a heated rod, and in this heated rod if you have multi-phase flow, so then the portion of the heated rod which is contacted by the gas bubbles will be having extremely high temperatures. Why high temperatures? Because if you subjected this heated rod under the constant heat flux condition, then from outside you are adding the heat flux at certain rate. Okay, but inside heat flux whatever is transferring, that will be function of thermal conductivity into del T by del N, temperature gradient in the normal direction. If you have gaseous contact with the wall, then thermal conductivity of the gaseous phase will be very less in comparison to the liquid phase. So because of this, even if you supply heat flux at constant rate from outside, inside fluid will be taking the heat flux at the lesser rate. So if inside fluid is taking heat flux at lesser rate, then overall surface temperature of the pipe will be increasing, because additional heat is being stored in the pipe surface. Okay, so and if you have liquid contact, then because of the high thermal conductivity, heat transfer rate will be fast, and if it matches well with the heat flux supplied, then temperature will be staying at the constant value. Or if heat transfer rate is fast in the liquid than the supplied, then even temperature can go down. Okay, so it means that it is not only the amount of the gas at a particular cross section which is of importance for designing various multi-phase flow systems, but the understanding of or the presence of distribution of different phases within the cross section is also important. Okay, so because of this we have to extend our analysis for flow visualization. So in our flow visualization, our interest will be that whatever phase density function data or whatever void fraction data we are obtaining, from that can we know what is our flow design, and second point is, even if we know, if we have identified the flow design, then can we exactly identify or construct the interface boundary. Is this one clear? So these are the two additional questions now which we will try to answer in addition to just obtaining the magnitude of the void fraction. Okay. So we know that if we have very complex interfacial structure between the two phases, like our fully dispersed flow, then we will be finding that we will be having multiple scattering of visible light if we are using optical proof, and near visible radiation, on which several visualization techniques such as laser interferometry etc. are based. And in these scenarios, our instrument must be able to distinguish between some physical property which is different for the two phases. So this already we have done even in case of our measurement of void fractions. Okay. So some of the techniques which typically can be utilized, already we have discussed about this, but still I am giving you a brief idea, that is radiography. So when we have used X-rays and gamma densitometer, so typically these type of techniques are used when we are dealing with the opaque samples. Now one important technique is there which is called as tomography. Okay. So what do you mean by tomography? Can you answer? I think few days back there was one institute colloquium also on tomography. Probably in the last semester. So anyone remember colloquium if you have attended? So a number of experimental techniques which allow to visualize a two-dimensional image of a given cross-section of the measured object. Okay, so tomography is a very generic term which just gives us idea that if you can visualize the 2D image of a cross-section, okay, then from that 2D image, whatever data you will be getting, that is nothing but a tomograph. Okay, so for example, you have a pipe. In the pipe, as we know that multiple bubbles are crossing, if at this cross section you can get some image, and this image can tell you that okay, this is how the interface is present at this cross section. Whatever technique is able to do that, we will be calling that technique as a tomographic technique. Okay. Now tomographic technique can be based on simultaneous measurement of physical property in several positions of the measurement plane. What is the meaning of this? Whenever we were interested in measurement of the local one-dimensional void fraction, what was our interest? In this pipe, we had put probe at certain location, and at that location we were trying to identify how signal is actually changing. Okay, that was giving us the idea of one particular location, phase density function at one particular location. If instead of this, I can consider a pipe, and in this pipe I can define multiple measurement points. All these cross points are what? These are my discrete measurement points. And in all the points, if I simultaneously measure phase density function, what will happen? At each and every point, I will be knowing about whether I am having gas present or liquid present. Is this point clear? So if I can devise some arrangement with the help of which I can create large number of measurement points within the cross section, okay, and then for this large number of measurement points within the cross section, simultaneously I can determine the value of corresponding phase density function. Then corresponding to this, at each and every point I will be having idea that this point is in contact with gas or it is in contact with liquid. All are clear with this point? So this is my starting point of the tomographic techniques. Okay, so in tomographic techniques, initially we have to obtain the value of phase density function at different finite number of points within the cross section. Okay, and later on, after we have this raw data, then we will be applying certain mathematical techniques with the help of which we can reconstruct the interface profile. All are clear with this point? So this is the starting point of the tomography, that we should have simultaneous measurement of any physical property, and of course that physical property I am designating it with the phase density function. Okay, a generalized definition, and this we have to measure at several positions on the measurement plane. Okay, and typically the use of tomographic techniques will be in internal behavior of the flows. For example, gas liquid 3-component flows in oil gas pipelines, gas solid flows, and mixing, separation, etc. So these are the applications of tomography, and this is useful for online monitoring and control of industrial processes. Okay, so what is the why this online monitoring is required? Can you tell me? So typically when chemical and process industries are running, so what we have to do? We have to supply reactants at certain controlled rate, and corresponding to that we obtain the products. If there is any change in the concentration of the reactants, then ultimately whatever product we are getting, that will be actually affected. And under certain scenario, it can happen that changes in the concentration of the reactants beyond the safe limits can also lead to accidental scenario. Okay, for example, there can be, if some exothermic reaction is taking place, there can be enormous amount of heat release which can lead to overheating of some failure and incident of fire, etc. Okay, so it means that whenever we operate in the chemical and process industries, where operation is continuous round the clock, okay, there online monitoring of the industrial processes is very, very important. Even in case of your, say, coal based thermal power plants, so you cannot stop a thermal power plant in between and then correct the thing and again switch on the power plant. Why? Because you have large number of components and each of the component have their own thermal inertia. Okay, for example, if you are operating boiler, if some fault has come in the furnace of the boiler, okay, so in that scenario what will happen? You have to first stop burning the coal. Once you are stopping burning the coal, it may happen that your furnace was initially at a temperature of 700 or 800 degrees Celsius. Now you have to allow the furnace to cool first to the condition of room temperature, so that you can access that location, and then you can repair the fault. After repairing the fault, once again whenever you are going to start it, then from reaching to a temperature of 700 or 800 degrees Celsius from the ambient temperature, again it will be taking a significant amount of time. So typically a thermal power plant, if you have to stop it, coal based thermal power plant, if you have to stop it and then start again, it may take time period in the range of 15 days to 1 month because of its thermal use. Okay, so likewise, if you have any process, okay, industrial process industry, so depending upon the nature of the industry and nature of the processes involved, because we will be having large number of multiple components which are simultaneously connected to each other and then simultaneously operating under the controlled conditions. Okay, so it is not feasible that at some point of time we have taken the sample of the measurement and then we have stopped the plant, corrected the thing, and then again we have actually started. So what we have to do, while process is running, during the process itself we have to put large number of measurement instruments at several locations wherever desired, and then by doing the online monitoring we have to actually take the corrective measures. Is this point clear? So that's why typically in chemical industries where multi-phase flows are involved, we have to do online monitoring, and tomography can be useful under such scenarios.
Sir, in tomography, whether like it is naming the fluid also like kerosene and water is flowing, or only give only two things are flowing, like
Only two things, okay,
it will
which
not
have,
differentiate.
yes, it will not be, it will be differentiating between kerosene and water, okay, but it does not know what is kerosene, what is water. It only tells that this is the phase where one type of characteristic behavior is observed, and this is the phase where other type of characteristic behavior is observed. Okay, basically your measurement techniques does not know the
Actually,
actual nature of the field. These are just based on the data whatever you are providing. So you know that, okay, if this much value of capacitance is observed, this is for water. So you can tell that this is water. But that will be simply telling that, okay, for this we have this much capacitance, for this we have this much capacitance. And then Depending upon your understanding or whatever the phases you are flowing, you have to decide that for this value, this phase will be water and this phase will be kerosene or this phase will be gas. Okay. Basically, this is giving you lot of data. So after data, whatever you have to interpret from that data, that you have to do by the way. Okay, so let's understand the general principle of tomography. Of course, tomography can be done using different ways like radiation attenuation, capacitance based, electrical resistance based. Okay, so over here I am giving you the generic principle. So this is the pipe. In this pipe, this is the two-dimensional plane which we have taken, and this two-dimensional plane will be having two coordinates x and y. Okay. Now here you can see a representative figure of phase distribution is given, where you can see this is your liquid phase and this is your gaseous phase. Okay. Mathematically, based on our mathematical understanding, if I say that I have large number of finite measurement points, then at each and every location I can determine the value of some indicator function. Let us consider the indicator function is f of x comma y. Okay, and this indicator function f of x comma y, which we are measuring, this we are doing the integral measurements. So the meaning of integral measurements is from all the sensing locations simultaneously we are measuring the quantity, and along with the simultaneous measurement we can also keep a record of this quantity for a finite time period. Is this one clear? And so this is the first part. What is first part? This I can say that this is my pre-processing. Okay, or I can say simply the raw data acquisition. After this stage, once you have raw data, it means you know the value of phase distribution function at each and every point. After that, what we have to do? We have to apply the reconstruction algorithm. Some mathematical algorithms with the help of which we can again predict the value of function f dash as the function of position, and corresponding to this, once I will be reconstructing, you can see what are my final shapes. What were the initial shapes? Initial shapes were circle, and finally what I am getting? Some rectangular or square arrangements. Why so? Because whenever there is a bubble, say, and in this bubble, if you have these four sensing points, so these four sensing points will tell you that these are having presence of gas, and in the surrounding sensing point it is telling that this is presence of liquid. So what is the easiest way to join these 4 points? To join with the help of straight lines. Okay, so that's why corresponding to this actual geometry, here you are getting this type of geometry. Now how I can improve this shape? Yes, so if I can increase the number of measurement points, and after increasing the number of measurement points, I can interpolate and I can define some curve using the higher order polynomials. Okay, so this all depends upon the different algorithms which are used in different techniques. Okay, and it is also to be noted that the multi-phase flow situations are so complex that whatever algorithm or interpolation function or mathematical parameters you have decided for one type of flow pattern, these may not work for the other type of flow pattern. So there you may have to again tune or recalibrate your algorithms so that you can actually apply that for other situations. Okay. So typically, because of the complex nature of the interfaces involved, the reconstruction of phases will be a tedious task, but particularly the development of mathematical system. Okay. Now, whenever we do the measurements, of course, for obtaining initial data, what we have to do? Either we have to use different sensors, and these sensors, depending upon the flow, will be behaving differently. So we have three different types of approaches. Some sensors are which are based on transmission techniques, some sensors are based on emission techniques, and some are based on deviation techniques. So in case of transmission technique, what happens? Because of the flow, some changes happens in the physical property of the emitted field. For example, initially we have seen in first method, if I am emitting some gamma rays, then whatever is the intensity at this point, E naught, after passing through pipe cross section, intensity will be E. So intensity will be changing while this ray is transmitting through this portion. In emission technique, what happens? We have some sensor which measures the radiation emitted by material inside the measurement cross section, which can be either spontaneous or induced by the sensor itself. For example, if you talk about high speed camera, okay, so what does camera does? Camera sends a light ray, that light ray falls at particular location, and from there it gets reflected. So this type of technique we are calling as emission techniques. Okay, and third is deviation technique. In case of deviation technique, if you are sending some ray, and because of the reflection or refraction, if it is changing, and based on that change, I have put large number of sensors along the pipe periphery, then if I can determine that whether it is going to this sensor or this sensor, corresponding to that I can define the curvature of the interface. So this type of techniques which employs this principle, these are called as deviation based techniques. Okay. And overall we know that whatever the previous schematic diagram I had explained about the general principle of the tomography, same diagram whenever we implement at the practical level, what we do, initially we have some indicator function phi of n. That indicator function will be passing through some algorithm, and corresponding to that algorithm we will be getting f dash xy. For example, corresponding to this circle I am getting a square. Okay, so this was the initial indicator function. After using some algorithm I have got f dash of xy. Now I can check this whether this f dash xy is identical to f of xy. How I can check? Say if I am having some other reference photograph of the cross section for which I have taken this data. Okay. So if I am having the reference photograph for the simultaneous measurement, then I can make this correlation, and if this signal and this signal are significantly different, then I can define some correction factor, and then with the help of some control algorithm I can keep on revising my output. So this is a simple representation of a closed loop based control feedback system which can be employed in the numerical algorithm for correcting it. Okay, but when we are using this closed loop based feedback system, for this we must have some reference image with the help of which we can actually calculate our system. Okay. Okay, now comes the idea that how we can employ different system for measurement of data. So mathematical algorithm is the second stage. Before that, what we need to do? We also need to measure the value of property at different finite number of locations within the pipe process. Is this not clear? So till now I have simply said that I will be having large number of measurement points, but if we have to take this type of measurements, what we need to do? We need to design some system or some experimental arrangement which can assist me in giving value of phase density function at all these different points. Is this one clear? Okay. So till now we are saying that at the pi cross section at large number of locations we will be measuring the indicator function. Okay. Indicator function means which gives indication whether you have liquid or gas present at that point. But if we have to get the data, then we have to also devise some mechanical arrangement which can give me this data. Okay. So first mechanical arrangement which we are talking about, that is electrical conductance tomography. Okay. One more important thing we have to also keep in mind, whenever deciding this mechanical system, we have to design it in such a way so that it does not causes significant change on the flow behavior. Okay, so if you place large number of optical probes, what will happen? Flow will be disturbed, so our flow pattern should also not be disturbed. Okay, so see here what we have. What is this? This is array of electrical wires. One array of electrical wires. Okay, and in this array all these wires are placed in a parallel arrangement with same spacing between the two wires, and typically the size of these wires is of the order of 1 micrometer. Okay, after this I have taken another array of wires which is at certain angle, and then there is third array of wires which is at another certain angle, and then all the wires are parallel. Another point is all these array of wires are not lying on a same plane. So these are segregated by some axial distance. Okay, for example, if this is my pipe, the first array is lying at this location, second array is at certain distance from the first one, and third one is at certain distance from the second one. Okay, and these distances are also very small, of the order of few micrometers. Is this one clear? Now what will be happening? All these arrays are separate parallel wires. One is this parallel wire, other is this parallel wire, and third one is at certain angle, other third parallel wires. Okay. If you consider a bubble which is of size 5 micron or 6 micron, so what will happen? This bubble of some micron size simultaneously will be making contact with all the wires. Okay, at certain point of time it will be simultaneously contacting the all wires in contact. So whenever it is simultaneously contacting all wires in contact, corresponding to this, whatever signal is, that is my one data point. Is this one clear? Have you got the idea? Basically what will be happening, if you have wire separated by some space, if electrically insulating material is there, then value of current signal which will be passing through the wires, that will be less. But if a good electrically conductive liquid is in contact with these three wires, then the value of electrical signal which you will be obtaining, that will be large. Okay. However, from the geometric arrangement, you can tell that how wires are arranged. Okay. So in this way, at each and every location of the crossover of these wires, I can determine the value of phase density function. Is this point clear? Now, this circuit can also further be simplified in order to design the reconstruction algorithm. How? Like this. Here you can see this is the spacing between the wires, and in some portion of the wire you have liquid contact up to length L1, then in remaining portion you have liquid contact up to length L2, and in between you have gas contact. Okay. Now in between the two wires, depending upon the liquid fraction and the gas fraction, resistance of the circuit can be defined. Is this point clear? I can define the individual resistance between the set of two wires depending upon the contact. So if I can define this resistance, then I can say that overall resistance will be summation I varies from 1 to n 1 by Ri into 1 by RLO, where LO is resistance of the wire when one particular type of fluid is completely flowing over the area of the wires. Okay, and this is then taken in terms of fraction of the length, Li divided by overall length. Okay, so likewise, in between each and every wire, you will be getting different values of resistances. And based on this resistances data, we can actually then utilize this for the reconstruction of the interface, and finally we can define the shape of the bubbles which we will be having here. All are clear with this point? So first type of mechanical arrangement. Right now I am not talking about the reconstruction algorithm. Over here our first attempt is to devise some mechanical arrangement which can give me the distribution of the phases present at each and every point. So like initial data of phase density function at large number of points. Now being all these wires of very thin in length, very thin in diameter, and placed at very narrow spacing between the plates, so for most of the multi-phase applications this will be working without causing much influence on the flow pattern. Okay. Then second type of tomography is acoustic tomography. So here in place of using the electrical signal, we will be sending the sound waves. So once we are sending the sound waves, then our measurement will be even more sophisticated, because in order to guide the sound wave in particular direction, we will be using only wave guides, and these are of very small thickness in comparison to the thickness of the wires. Let's also now discuss this. Let's quickly now discuss about how these signals can be used for phase identification. Okay. So if you have to use this signal for phase identification, initially what is our interest? Our interest is two things. First is phase identification and second one is phase reconstruction. Okay. So first let's talk about the simple thing, phase identification, and then this we will take from one of the research paper, and then quickly we will also discuss one case study about the phase reconstruction. Okay, and this is just basic idea of tomography, because different tomographic systems works differently. So depending upon the type of the system we are using, reconstruction algorithm and the measurement system may vary. Over here, the overall idea of this lecture is just to give you the overview of the tomographic techniques, that how tomographic techniques behaves, okay, and how this works. So first case study which I will be taking over here, that is on phase identification using the optical probe. So what is there? This is a pipe, and in this pipe from the top there is one laser light source. This laser light is passing through the transparent pipe, because we are using the optical technique, so pipe should be transparent. And at the bottom there is one detector. So typically for detecting laser light or visible light, we use the photodiodes. Okay, whenever light falls on a photodiode, it generates the voltage. So this is the mechanical configuration which is used, and this is used in a horizontal pipeline. Okay, now you can see in this horizontal pipeline, two arrangements are done. From here inlet is there, and from here we have outlet. Okay, and this is the source, this is the detector. Now if you initially fill this pipe with water, so your complete height h by d ratio will be equal to 1 when complete pipe is filled with the water. So corresponding to this h by d ratio, you can see this is your voltage signal. Okay, now what you have done, you have slowly started taking out the water. If you take out the water from this outlet, what will be happening? Water level inside the pipe will be going down, and if you don't supply any other liquid from the top, then the space displaced by the water will be occupied by the air, and then we will be having presence of air water interface in between. Okay, so because of the air water interface, now we will be having some reflection of the light. So because of the some reflection and refraction, the value of light intensity will be decreasing, which we will be receiving at the detector. Okay, so here you can see when h by d ratio is decreased, then this is the decrease of the signal for air water. However, is this change of signal sufficient enough to come to any conclusion about the height of the interface? So this signal at this point is not clearly distinguishable so that I can predict what is the height of water present inside the. Is this one clear? Now, when same thing is done, but in place of air and water, now kerosene and water are used as the two fluids. So whenever now you will be decreasing the water level from the inlet, you will be supplying equivalent amount of kerosene. Okay, now your interface is not of air and water, but interface is of kerosene and water. Moreover, the light absorption coefficient of kerosene is higher in comparison to the light absorption coefficient of the water. Whereas for air and water, these light absorption coefficients were almost in the same limit. Okay, so now you can see that whenever you are decreasing the height of the height of the water, then corresponding to that, the value of signal is also decreasing. Okay, so it means that when light was completely passing through water, then the intensity of light at this point was more and you were getting higher value of voltage. But when the entire tube is filled with kerosene, then corresponding to that intensity of light is less, because it is light absorbed by kerosene is more. Okay, and we have got less value of voltage signal at the output. Okay, and you can see how this nature is changing. This nature is changing something like this. So basically, in our basic optics, there is one law which is called as Weir-Lambert's law. What does it tell? It tells that intensity of light will be changing in exponential fashion with the position and the coefficient of a particular interface. Okay, is this one clear? So because of this law, whatever the change of voltage signal we will be observing with non-dimensional depth of water, this change will be taking place in a exponential. Okay. Now, initially, because our idea is not to measure directly the height of the interface, but our interest initially is only to measure the type of the flow pattern. Okay. So, whenever you have a pipe, and in the pipe, if in the top you have one type of fluid and in the bottom you have other type of fluid, and your flow pattern is smooth, stratified. Okay, so you have flow which is taking place from left to right, and during the left to right while flow is happening, your interface is almost flat. Corresponding to this, whatever the voltage signal you are getting with time, that is something like this. Instead of this, if you have bubbly flow situation, then you have this type of signal. Okay. Now, by just looking into the raw signal between pure stratified and dispersed flow, I can have some idea that whenever this type of signal I am getting, it means my flow will be smooth, stratified in the pipe, and if I am having this type of signal, then flow will be bubbly or dispersed in the pipe. Okay. Here you know why this type of random signal is coming, because whenever it is passing completely between the bubbles, then your strength of the signal is high, and whenever bubbles are crossing, then reflection of the light is taking place and strength of signal is actually decreasing. Okay. It is very easy to compare the difference between stratified and dispersed flow by just looking into the raw value of the signal. Okay, but if we try to go for some more advanced situations which are closely related to each other. For example, here you have a stratified flow, and here you have which type of flow? Wavy stratified flow. Okay, now between this signal and this signal, if I don't give you these photographs, can you tell me which one will be good, which one will be corresponding to which flow situation? Here it is extremely difficult to exactly specify the nature of the flow. Okay, so under this scenario, what we can do, we can perform further statistical analysis of the signal, and depending upon the statistical analysis, we can come up with some specific statistical features of the signal which have identical behavior for one particular type of the fluid. For example, here you can see for this type of flow, the peak value of the signal is large and its standard deviation is less. On the other hand, when I am having wavy stratified signal, then peak of the signal is less and standard deviation is large. Okay, so it means if you have large standard deviation, then your flow pattern will be changing from smooth stratified to wavy stratified. But if you have very narrow standard deviation and large peak in the raw signal, corresponding to that, you can say that your flow will be in the stratified design. Okay, so basically what need to be done when you are calibrating this device, you need to perform some analysis of the data, and you need to identify some characteristic features of the data which are unique to a particular type of flow pattern. Okay, so whether you operate in smooth flow regime at velocity of 0.07 meter per second or velocity of 1.5 meter per second, if the identified characteristic of the signal is unique, then always you will be able to describe the behavior of the flow pattern. Is this point clear? Now you can see the difference between two bubbly arrangements. Okay, so this is a bubbly arrangement with large slugs present, and this is a bubbly arrangement with small bubbles which are significantly distributed. So now you can see the fluctuations in the signal will be so high that mean of the signal is very less and standard deviation is significantly high. So your signal is distributed over the large portion. So corresponding to that, we can say that our flow behavior is actually dispersed. Okay, and this is the comparison of the flow pattern map, which is based on visualization and based on the data obtained from the optical signal. Okay, so here you can see these are the phase boundaries corresponding to what? Corresponding to the visualization based measurements. Okay, and these data points are coming from the optical measurements. So here you can see that though it is able to give you the better idea, but typically near the transition zone you may have some overlap of data between the different objects. Is this not clear? However, in most of the bulk portion of the flow design, your analysis of signal, but the way it is done in the previous discussion, it is able to give you the idea of the flow design present in the system. Okay. So we will stop now, and in the next class we will quickly discuss about one case study from where the data based on the height difference can be utilized for reconstruction of the interface.